Hello everyone, this is a short little lesson on the concept of work. Now, energy is often defined as just the ability to do work, right? It is kind of that ambiguous ability to do something. But what is work, right? Well, back in very early years, as we were trying to introduce this concept, usually we introduce this as simply to cause a change. Right, which is not a wonderful definition, but it tends to work. But more specifically, it is defined as the product of force and displacement, right? Which essentially means that the formula is just work is equal to F times D, right? W is equal to FD. And this is on your formula sheet, where work is in joules because it's basically just used energy. Forces in newtons and distance in meters. So a newton meter is a joule. Okay? So if we were to define it in our own words, well, there's lots of ways you could do that. Typically, I'd just say when a force moves an object, right? You're going to have your own definition, but this is just kind of my own words, where it's the force moving an object, that is the distance. Now, a couple of things here that you should be aware of. I want to highlight them. First of all, there must actually be a force exerted on an object. If it is just moving due to inertia, no work is being done. Right? Now, the force must be acting in the same direction as the movement. Okay? If I were to, let's say, take this object and I hit it this way, and then all of a sudden it decides to shoot off this way, well, what have I actually done there? I've applied a force this way, it's moved that way, no real work is being done, right? At least part of the force must be in the same direction as the displacement. And so the force used to calculate work is the applied force. That's a little typo there. So it's the applied force that we're going to act on the object. That's what we're going to use to calculate what's going on. Not the net force, but the applied force. So please correct that little typo in your books there. If you're watching this in later years, I've probably already fixed that. So let's take a look at example number 1. A 15 kilogram object is lifted at a constant velocity from the floor to a height of 1.5 meters. How much work is done to lift the object? Well, let's take a look. So free body diagram. There are two forces acting on this, the force due to gravity and the force applied to this object. Now, because this is moving at a constant velocity, these two forces have to be equal and opposite. Right? So the force applied is going to be the same as the force of gravity, just acting in the opposite direction. So essentially what we can say is that the amount of work done, again, which would be FD, but this work is the same as MAD, which means work is in fact mad. Yes, you can pause the video because I know you're laughing hysterically right now. 15 kilograms. The acceleration we're going to use here is 9.81 meters per second squared, and that's just because we're counteracting gravity, and a distance of 1.50 meters, and so the units here, kilogram, meters squared, second squared, or joules, and you should get 221 joules. Well, taking a look at the next example here, we've got a 10 kilogram object moved horizontally 5 meters across using a force of 3 newtons. How much work is done to the object? Well, here we've got our object again. We're applying 3 newtons of force this way. Now, we've got a normal force, we've got a gravitational force, but these forces actually don't make one bit of difference to what's going on here, because they are not in the same direction as the movement. This object is moving 5 meters this way. And so the work is equal to force times displacement, right? We're using the 3 Newton force multiplied by 5.0 meters. And so the amount of work done is 15 joules. You don't worry about the 10 because it's not operating in the same direction as the displacement. Taking a look at our third example, we've got a 3 kilogram object that is held 1.2 meters above the floor for 15 seconds. How much work is done? Well, again, we've got an object, force of gravity moving this way, and we're applying a force in the equal and opposite direction here. Thing is, though, is because it is just being held there, right? It doesn't matter about the location, the fact that this is 1.2 meters above the floor, it's staying there. So yeah, we got this force that's being applied, but the distance is 0, which means the amount of work done is 0 joules. We don't even need to worry about calculating what force that would be. So taking a look at a little bit more complicated situation here, where we've got this object, this 50 kilogram box. Now it is being pulled 35 degrees by a 90 Newton force this way. Now, some of this force is moving this way. Some of this force is actually lifting it off, which is actually going to reduce the amount of normal force and thus the amount of friction that this box is going to see. But in order to figure out how much work is done, okay, we're actually going to need to use this force. So cos theta is equal to adjacent over hypotenuse, or cos 35 is equal to that adjacent over 90. So 90 cos 35 is equal to that amount of force that we're looking for, and you should wind up with 73.7 newtons in the adjacent direction. And that, as it's being dragged along 11 meters, is the amount of force that we're using. Right? So that's 73.7 multiplied by 11 meters. That gets you 810 joules of work. Okay, last example here, we've got a car traveling 61 kilometers per hour, being brought to a stop while skidding 42 meters. Well, we know that the amount of work is going to be equal to the force times distance, which would be mass times the acceleration times the distance. Well, we've got the distance, but we don't know what the acceleration is. So, a couple of things. First thing we're going to do is we know that the initial velocity is 61 kilometers per hour. The final velocity is 0, and we know that the displacement is 42 meters, or distance actually traveled. We need to convert this to meters per second, which means it's the same as 61,000 meters divided by 3,600 seconds in an hour. And that means it is traveling at 16.9 meters per second. Okay, we're still looking for that acceleration, so Vf squared is equal to Vi squared plus 2AD. Vf is 0 squared is equal to 16.9 squared plus 2A42. When you calculate this out, you should get 3.42 meters per second squared. Now that's negative because this car is traveling this way, but the acceleration is this way, which is why it's going to stop, and so it's going the opposite direction. We're really just work, though, being a scalar quantity. We're not really worried about that. The mass of this car is 1,385. The acceleration is 3.42 meters per second squared over 42 meters. Means the amount of work done is going to be 1.99 times 10 to the 5 joules. Okay, hope that helps. If you've got any questions, please let me know. Take care.